Continuing our journey of the solar system, we head to the next planet on the path, Jupiter. However, before getting to it, we have to pass through an often neglected region, the Asteroid Belt. This is the smallest and innermost known circumstellar disk in the solar system. It contains a number of solid, irregularly shaped bodies and extends irregularly over the space between Mars and Jupiter, spinning as a whole around the Sun. The overall mass of the belt is about 2.2 billion of tons. Moreover, all this mass is more than the half concentrated into the four main asteroids, Ceres, Vesta, Pallas, and Hygiea. Here we come to the guest of today's overview. Jupiter, the gas giant with a mass more than 2.5 times that of all the other planets in the solar system combined. Jupiter is by far the largest planet in the solar system, more than twice as massive as all the other planets combined. Jupiter's stripes and swirls are actually cold, windy clouds of ammonia and water, floating in an atmosphere of hydrogen and helium. Jupiter's iconic Great Red Spot is a giant storm bigger than Earth that has raged for hundreds of years. Jupiter is surrounded by dozens of moons. Jupiter also has several rings, but unlike the famous rings of Saturn, Jupiter's rings are very faint and made of dust, not ice. Being a gaseous planet, you can easily imagine that its mean density is not very high, 1/4 of the Earth's. Indeed, Jupiter is primarily composed of hydrogen, followed by helium. As you may have heard if you followed our articles and video on ESA's JUICE mission, a system of 95 known moons and probably many more orbit around this giant planet, and famous are the four large moons, Io, Europa, Ganymede and Callisto. Returning on the planet, the ongoing contraction of Jupiter's interior generates more heat than the planet receives from the Sun, so there is a very interesting heat balance over this body, with a strong contribute coming from inside the planet. But where does this heat come from? For sure from the huge pressure generated on the molecules of hydrogen, which is in turn generated by the strong gravity coming from the huge mass of the planet. So, a lot of gas means a lot of mass, which turns into a lot of gravity which attracts the gas towards the center of the planet. This gas is then compressed, incrementing its pressure and temperature, giving birth to an interesting couple of effects: a strong heat from the planet's interior and the liquefying of the hydrogen gas due to the prevailing effect of pressure. There is possibly an iron-nickel core in the center of Jupiter. The mass of the core is probably equal to a few tens of Earth masses, and the core is surrounded by that layer of metallic liquid hydrogen, where the temperature is over 10,000 degrees Kelvin and the pressure around 3 million atmosphere. The outermost layer of the atmosphere contains also crystals of frozen ammonia. Through infrared and ultraviolet measurements, trace amounts of benzene and other hydrocarbons have been found, as well, while the interior of Jupiter contains denser materials. Yes, the hydrostatic equilibrium still holds on Jupiter. It is very interesting that the atmospheric proportions of hydrogen and helium are close to the theoretical composition of the primordial solar nebula. Even though the revolution period of Jupiter is about 12 years, the rotational period is much smaller. In addition, this number is different depending on the latitude considered, which means that on the equator the gases that compose the upper layers of the planet turn at a different rate than in the polar regions. Think that, as a mean value, it makes one rotation every 10 hours, so the planet's shape is an oblate spheroid. It has a slight but noticeable bulge around the equator. The belts are reddish or brownish, and the motion of the gas inside a belt is downward, while the gas flows upward in the white zones, restoring this dynamic equilibrium. The clouds are slightly higher and have a lower temperature than the belts, but strong winds, or jet streams, blow with speeds up to 600 km per hour at some places in the upper atmosphere, while in the lower layers can reach up to 2,000 km per hour. Do you remember that the heat comes from the inside more than from the Sun? Those winds, stronger in the lower atmosphere than in the upper, are a consequence of this phenomenon. Another consequence is the strong motion of convection that comes from the internal layers of the planet, moving large masses of liquid metallic hydrogen and generating the strong magnetic field of the planet. Moreover, a famous peculiarity of this atmosphere is the so-called GRS, Great Red Spot. Now stop a try to think how big it is. It is indeed 14,000 kilometers wide and between 20 and 40,000 kilometers long. Some smaller red and white spots can also be observed on Jupiter, but their lifetime is generally much less than a few years. It is not known what causes the Great Red Spot's reddish color. Hypotheses supported by laboratory experiments suppose that it may be caused by chemical products created from the solar ultraviolet irradiation of ammonium hydrosulfide and the organic compound acetylene, which produces a reddish material, likely complex organic compounds. On the 25th of February 1979, when the Voyager 1 spacecraft was more than 9 million km from Jupiter, it transmitted the first detailed image of the Great Red Spot. Cloud details as small as 160 kilometers across were visible. The colorful, wavy cloud pattern seen to the left of the red spot is a region of extraordinarily complex and variable wave motion. In the 21st century, the Great Red Spot has been observed to be shrinking in size. At the start of 2004, its length was about half that of a century earlier, when it reached a size of 40,000 kilometers, about 3 times the diameter of Earth. At the present rate of reduction, it will become circular by 2040. The spot is confined by a modest eastward jet stream to its south and a very strong westward one to its north. Though winds around the edge of the spot peak at about 432 kilometers per hour, currents inside it seem stagnant, with little inflow or outflow. The rotation period of the spot has decreased with time, perhaps as a direct result of its steady reduction in size. So, that's all for today. If you liked this video, please leave us a like, it will greatly support us. And consider subscribing to our members club. It's free and you will access exclusive content for members only. See you in the next video.